Hey, what's going on, guys? Let's look at this problem right here. Here this question is asking, consider the magnetic core with an air gap as shown in figure 1. The core material has a relative permeability of 6000 and a rectangular cross section of 2 cm by 3 cm. The coil has 500 turns. Determine the current required to establish a flux density of B gap that is equal to 0.25 Tesla in the air gap. Consider fringing at the air gap by adding 0.5 cm to both the width and the depth of the air gap. Okay, now let's see how to do that. First, I'm going to write the mean length of the ion. The mean length of the ion core and the cross-sectional area, and the cross-sectional area, that's what we are going to calculate. Mean length is L, that is 4 times 6, double of this one 2 times 3, we have 2 times 3, so the double of this one is 4 times 6 because we are looking at the both side. So 4 times 6 minus the gap, that is 0.5, and that gives us the mean length, that is 23.5 centimeter. Now the next thing is we are going to calculate the cross-sectional area. The cross-sectional area can be calculated by simply multiplying this 2 centimeter and 3 centimeter. If we convert this one into meter, this is going to be 2 times 10 to the power of minus 2 multiplied by 3 times 10 to the power of minus 2, and that gives us 6 times 10 to the power of minus 4 meter square. Now the next thing is we are going to calculate the permeability of the core, mu core. That can be calculated using mu r times mu naught. Mu r is given in the question, 6000, and mu naught is a constant value, that is 45 times 10 to the power of minus 7. And if we calculate this one, that gives us 7.54 times 10 to the power of minus 3. Now the next thing is we are going to calculate the reluctance. Reluctance is equal to L core divided by mu core times A core. Mu core times A core. Now here we have I'm going to add some notes. The flux lines tend to bow out in the air, air gap as shown in figure. This is called fringing. Thus the effective area of the air gap is larger than the effective area of the air gap is larger than that of the ion core. Customarily, we take this into account by adding the length of the air gap to each of the dimension of the air gap cross section. So that gives us A gap is equal to 2.5 times 3.5 centimeter squares. We just add 5 centimeter to both sides. 2 centimeter, we add 5 to that, to 0.5 to that, 3, we add 0.5 to that, and that gives us 8.75 times 10 to the power of minus 4 centimeters meter square, because if it's 10 to the power of minus 4, it means we convert this one into centimeter square to meter square. Okay, now we are going to calculate the mu gap. Mu gap is basically the mu naught, because in the air it's always mu naught. 45 times 10 to the power of minus 7. Now the next thing is we are going to calculate the reluctance of the air gap. Reluctance of the air gap is here, instead of L core we put L gap right here, and mu gap times A gap. Mu gap times A gap. L gap is L gap is the length of the gap, that's 0.5 centimeter, and that one divided by mu gap times A gap, that's gives us 4.547 times 10 to the power of 6. Then we are going to calculate the total reluctance. Total reluctance, that is 5.199 times 10 to the power of 4 plus 4.547 times 10 to the power of 6, and if you add these two together, that gives us 4.552 times 10 to the power of 6. Okay, now the next thing is we are going to calculate the flux. Flux is given by B gap times A gap. B gap is 0.25 times A gap is 8.75 times 10 to the power of minus 4, and when we calculate we will get 2.188 times 10 to the power of minus 4 Weber. Okay, now we have calculated the phi, that's flux. Here the question is asking to calculate the current. Current can be calculated by this formula. I is equal to J over N. J is MMF. To calculate J, we have an equation. Okay, let's get rid of this one. To calculate the J, we have an equation. J is equal to phi times R. We calculated the phi right here, that is 2.188 times 10 to the power of minus 4, and R is calculated right here, 4.552, the reluctance, times 4.552 times 10 to the power of 6, and that gives us 996. Now the current can be calculated using this formula. Current is equal to J over N. J is 996 divided by N is number of turns, that is 500. So if you divide this one by 500, that gives us 1.992 ampere. I is equal to 1.992 ampere, and that's the current. And that's how we do this kind of problems. I hope you guys find this video helpful. Thanks for watching, and if you are trying to learn electromechanical system, there are a bunch of videos in my playlist. I hope you guys watch that too. Don't forget to subscribe. See you next time.